Bismillahirrahmanirrahim. Now chapter 16, wave motion. Right, in this chapter we will continue crossing the bridge we mentioned at the beginning of chapter 15. Wave motion represent a phenomena in which a disturbance propagates through a medium. Okay, the disturbance carries energy from one point to another, but there is no matter that moves over the distance. So means that the medium of the wave remain within the same location, but then the energy is going to be transferred. Alright. So if you refer to this diagram, okay, this is one of the simplest example for the propagation of the disturbance. Okay, where we have, okay, a stretch string here, okay, as the medium, and the source of it is the hand that going to shake the stretch string, okay, that going to make a pulse that moving or passing through the stretch string. So the pulse is representing the energy or the wave being being transferred from one point to another point. So this is one kind of a mechanical wave, the simple mechanical wave. It must have source, which is a hand, okay, the one that vibrate, the medium, which is a string here, and also the physical mechanism connection between the source and the medium. Alright, this is a must for mechanical wave. Right. The portion of this string, of this part of the string, is not traveling to this region, okay, but the pulse created is going to travel from one point to another and then finally reaches the end of the string. So this is the meaning of how wave is a kind of disturbance where the energy within the disturbance is moved throughout the medium, but then the medium itself vibrating within the same location. Okay, so this is also the same analysis. Okay, if we consider only one single point P here, what's going to happen to this point P is going to vibrate, okay, up and down, whereas the motion of the wave of the pulse is to the right. If you still remember these two type of disturbance or propagation of disturbance, okay, this one is transverse, right, that we discussed previously in previous slide, and this one is longitudinal. What is the difference? For transverse, the motion, the movement of the medium is perpendicular up and down here to the motion of the wave. The pulse is moving to the right. Okay, the pulse or the wave is moving to the right, but the medium is moving up and down, which is perpendicular to the direction of the motion for the wave. So up and down, okay, and the other one is to the right. This is the wave motion. This one is the medium motion. This kind of wave, we call it transverse wave. But then for this example, if let's say spring here, okay, and then you're going to move the spring, compress the spring left and right, okay, and then the region, the compression region and rarefaction region going to be traveled throughout the spring until this point. So the motion of the medium, okay, left right like this, is parallel or anti-parallel, parallel and anti-parallel to the motion of the pulse or the wave. For this kind of propagation, we call it longitudinal wave. But in nature, we have lots of combination of transverse and longitudinal displacement. For example, wave within surface of the ocean, right? Surface water wave in ocean. Okay, when water travels, right, on surface of a deep water, it must a deep water, okay, elements of water at surface move in nearly circular path, like this, nearly circular path, okay, as in figure. Disturbance has both transverse and longitudinal components. Okay, the transverse displacement represent variation in vertical position of the water element. So sometimes it's on the crest, isn't it? Sometimes the particle or the water on the throw. Okay. Longitudinal displacement represent element of water moving back and forth in a horizontal direction. Okay, we have both. Combination means that. Okay, point where displacement of element from its normal position, which is the crest of the wave, and for the throw is the lowest point. Right, so this is as a recall only. Another example of the combination is actually earthquakes. Okay, earthquakes represent disturbance that result in seismic wave, we call it. Two types of transverse and longitudinal. We have a longitudinal wave, also known as P wave, stand for primary, because it's the speed of it bigger. It travels faster than the transverse wave. The transverse wave, called the S wave, stand for secondary wave. Okay, the speed is lower, which is about 4 to 5 kilometer per second. Okay, by recording time interval between the arrival of two types of the seismograph, at the seismograph, the distance from seismograph to point of origin of wave can be determined. Where the radius of imaginary sphere centered of seismograph origin wave located somewhere on that sphere. That is how they read or analyze, okay, the seismic wave, okay, and define, okay, where the earthquake going to occur. Wave function. We're going to consider a pulse, okay, that going to travel to the right on long string, okay. At any time, pulse can be represented by some mathematical function, y as a function of x and t. What is y? This is y, okay, this y, okay, and then it's depending on the x, isn't it, as well as time. Okay, so we can put it like this: y as a function of x and t, okay, is equivalent to, right, so this is wave function, okay, because we are talking about the pulse. The pulse itself is a wave. Y x minus vt, and the t is 0. Why is it x minus vt? Because after a certain time of t, after t time, right, now the position of the crest itself, already displaced to this point, which is from here to here. The distance traveled, the x, is equivalent to vt. How come? Because v is equivalent to x over t, right? So after t time, okay, the x equivalent to v times t. So it's actually talking about this x. Okay, so point here initially is at this point and finally at this point, isn't it? So the crest just now. Okay, so the distance traveled after t time, at t equivalent to t, okay, the x is equivalent to vt. That is why x minus vt, because it's traveling to the right. Okay, and simply, if the time is 0, at t equivalent to 0, y as a function x and t is equivalent to, right, the function of the f, okay, times with the x minus vt. Okay, if it is traveling to the right, okay, but if it is traveling to the left, so y as a function of x and t is the function of itself, okay, x plus vt because it's to the left. Alright. What is the meaning of the y? Okay, so if you consider the element p here, okay, in figure, is identified by particular value of its x coordinate, right? Okay, so as the pass through or moving or passes through point P, okay, the y coordinate of this element, okay, going to be increased initially at 0. Okay, after the point P is passes through this one, then the point P is changing in terms of its y coordinate, right? So reaches maximum, is going to reach maximum, then decreases to 0 back. Okay, and the wave function, what is the wave function? Is this one, okay, represent the y coordinate, the transverse position of any element located at position x and any time t. Okay, imagine viewing pulse at particular instant of time where we're going to take a snapshot, okay, see something like figures, okay, given here, okay, geometric shape fx, okay, of a pulse at particular instant called waveform. And now we move to sinusoidal wave. Okay, so this is actually talking about whenever you're going to shake the end of the rope up and down continuously, let's say. Okay, so when you make it continuously, it's going to move in simple harmonic motion. Okay, so from that, you're going to produce, okay, sinusoidal wave actually, okay, as shown in this figure. Shaking end of a rope, the rope in simple harmonic motion leads to sinusoidal wave, okay, where we have close relationship between simple harmonic motion and sinusoidal wave function as before. And you see previously, okay, we already shown that simple harmonic motion can be expressed in terms of sinusoidal wave. Alright, sinusoidal wave, this is actually the simplest example of periodic continuous wave as I mentioned just now. Okay, it can be used to build more complex wave. How? When you combined. Okay, so if you refer to this figure, okay, you have a brown curve and also the blue curve here, or wave here, sinusoidal wave here. The brown curve represents snapshot of traveling sinusoidal wave at t equivalent to 0. Right. The blue curve is representing snapshot of wave at some time letter t, at t equivalent to t. So initially, let's say this position, this point, okay, this crest, okay, at this position. After t time, okay, it's already moved to this position. Okay, so it's already traveled x distance, which is equivalent to vt. Right, and we consider the v is a constant v. Okay, and the wave is moving to the right. All right. It is important for us to differentiate between motion of the wave and motion of the elements of the medium. For this case, the motion of the elements of the medium is up and down, and the wave is traveling to the right. Okay, this is what we call traveling wave or propagating wave. From this figure, you can see here, okay, for one complete crest to crest, the distance between crest to another crest is known as lambda. We call it as wavelength. Okay, it must be the distance between adjacent crest or adjacent throw, or the same point. Let's say you have it here, from here, let's say from here to here, also 1 lambda. It must be one complete oscillation or circle or vibration or waveform, right? And the period, okay, if you are referring y versus t now, okay, and the period also the same. It's time taken to complete one oscillation or vibration, or time interval required for element to complete one cycle of its oscillation, and for the wave to travel one wavelength, also the same. So what is the formula of the F? If you recall, F is equivalent to 1 over T. Alright. And next one, okay, if you refer to this figure, what information that we can extract from this figure? The first thing first is the distance between two adjacent crests or two adjacent throw is 1 lambda. Okay, 1 lambda is called as wavelength. And then maximum displacement from equilibrium position to maximum displacement of position is known as amplitude. Okay, this is for the medium to be displaced. Okay, so just now we have y as a function of x. Let's begin with at t equivalent to 0 is equivalent to a sine, okay, must be a constant, right? Previously we put it as omega, but this is a wave, slightly different. First thing first, we need to determine what is the constant. So we put it as a, the unknown. Okay, from here, right, if let's say your x is 0 as well, initial condition, okay, a sine 0, isn't it, becomes 0. Okay, one thing. For one complete half of the wavelength position, okay, y is equivalent to lambda over 2, right? Still at t equivalent to 0, equivalent to a sine, okay, a, your x right now is lambda over 2, okay, and equivalent to 0. Okay, and from here, a lambda over 2 equivalent to pi. Why is it so? Okay, because half of the wavelength is actually here. This is lambda over 2. Okay, and lambda over 2 for one complete, this is equivalent to pi, half of the circle, isn't it? And complete one circle, another pi. Okay, that is why is equivalent to pi. Consequent of it, we may rearrange, put it like this, 2 pi over lambda. And y, again, we are going to rephrase it as a function of x whenever t is 0 is equivalent to a sin 2 pi over lambda times with the x. Alright, so if let's say our wave right now is moving to the right, it's basically moving to the right, this is the v of the wave. So in general, our waveform or function x at time t is equivalent to a sine 2 pi over lambda x minus vt. Okay, why is it minus vt? Because it's traveling to the right. Okay. Okay, and now we're going to proceed with v equivalent to, as we know, delta x over delta t. This is actually lambda over period for one complete oscillation. So now y as a function of x and t is equivalent to a sine 2 pi x over lambda minus t over t. Bear in mind, okay, we can have a term of, okay, k equivalent to 2 pi over lambda, and omega, not to forget, 2 pi over t, which is also equivalent to 2 pi f. What is k? Okay, k is wave number. What is wave number? This is actually this part. Okay, a constant, just a constant, right? And how come this one, how come it's named as wave number? Okay, previous scientists want to simplify it, okay, this constant, so it's symbolized by k. Okay, we call it wave number. All right, and then this is already known from our previous lesson. Now our y can be written in terms of this, in terms of simplified version, a sine kx minus omega t. Okay, and the speed of the wave is equivalent to omega over k. Okay, and also from here, what is our omega? Okay, our omega is 2 pi f right, divided by k. What is our k? Is 2 pi over lambda, right? So you are going to have the v in terms of lambda f, another form. Okay, therefore now our y as a function of x and t can be written in terms of this in general. Okay, why is it plus phi? Plus phi whenever the t is not 0. Okay, whenever the t is not 0, we could have any information of phi. All the condition that we derive here from this to this to this previously, we consider the t is 0, right? Okay, so this is the general equation where we consider at any t. That is why we do have the phi. Right, so example 16.2, a traveling sinusoidal wave. A sinusoidal wave traveling in the positive x direction has an amplitude of 15 cm and a wavelength of 40 cm and a frequency of 8 Hz. The vertical position of an element of the medium at t equivalent to 0 and x equivalent to 0 is also 15 cm as shown in the figure. Okay, so 15 cm, right? Amplitude also 15 cm. Find the wave number k, right? Period t and angular frequency. Here is actually omega and the speed of the wave. Right. First, we may begin with 2 pi over lambda is a k. Okay, and we know that 2 pi radian over 40 cm, okay, is equivalent to 15.7 radian per meter. Okay, and also t equivalent to 1 over f 1 over 8 second, which gives you 0.125 second. Based on information given, we may extract these two information firstly, then followed by omega equivalent to 2 pi f equivalent to 2 pi times 8, isn't it? Therefore, you will have 50.3 radian per second. And next one, for V equivalent to lambda F, you have your lambda equivalent to 40 and your F is 8 seconds per second. Therefore, finally, your V is 3.2 centimeter. Meter per second. Next one, part B, determine the phase constant, or the symbol supposedly phi, and write a general expression for the wave function. Okay, so to figure out the phi, we must use this information, 15 sine, when the x is 0, right? Then we figure out the phi, because phi is initial condition whenever x equivalent to 0. So sin phi equivalent to 1 from here. Therefore, phi is equivalent to pi over 2 radian. Right, now the y as a function of x and t can be written in terms of kx minus omega t plus pi over 2. Okay, and this is actually equivalent to a cos kx minus omega t only, if we convert from sine to cos function for the y, right? So why we need to convert it into cos? Because the shape of this also can be referred to as a cos function. So now, okay, our y can be expressed in particularly this form. Okay, sinusoidal wave on a string. Okay, so again, if we refer to this diagram, this is figure A, figure B, and so on. In this diagram, okay, the original shape of it, the initial shape of it is sin. Okay, if that's the case, then our y, okay, in simple, A sin kx minus omega t. Alright, and then for Vy, okay, what is Vy? Just now we are talking about V. V is the velocity or speed of the wave. But Vy, okay, is actually the speed of the particle along y. Okay, so the speed or the wave, the velocity of the particle along y, the medium itself, is dy over dt. Okay, where we consider x in constant condition. Right, we need to do partial differentiation, dy over dt. Why is it partial? Because our function here, the y is depending on x as well as t. Okay, so we are going to differentiate dy over dt partially. We are not considering the x. That's why we use this symbol. Right, and then it's equivalent to, okay, when you differentiate sin, you will get negative omega a cos kx minus omega t. Right, to have a along y, the acceleration along y for the medium must be dvy over dt, where again the condition is to consider x as constant. Okay, consequent of this, we are going to do partial differentiation of dvy over dt, okay, equivalent to negative omega square a sin kx minus omega t. Okay. So again, similar to the simple harmonic motion, when you want to have Vmax along y equivalent to omega a only. Why is it so? Because function here become 1 when you're talking about max. So you're going to have omega a. Right. When you're talking about acceleration along y and maximum, okay, originally is equivalent negative omega squared a sine kx minus omega t. So the whole bar of this, if we're talking about maximum, the function going to be 1. So if we're talking about magnitude, then it's going to be omega squared a. So we're going to do analysis model traveling wave. For traveling wave, we are going to do the details. Okay, from this figure, again, let's recall. Okay, the distance between one crest to adjacent crest is lambda. Maximum displacement from equilibrium position for the medium is the amplitude. And the V of the wave right now in this example of figure is to the right. Then, okay, our V equivalent to lambda over period. This is coming from which concept? Which is to distance travel over time taken. Okay, from here, the V also can be written as lambda F. Okay, and for Y, in general, sine kx minus omega t. Okay. Now we move to speed of wave on a string. Okay. Linear mechanical wave have a speed where it depends only on the properties of the medium through which wave travels. Okay. Wave for which amplitude a small relatively to the wavelength can be represented as linear wave. Okay, almost. Right. Okay, for this part, we are going to derive expression for speed of pulse traveling on a stretched string under tension T, okay, as in this figure. All right, we consider the pulse moving right with uniform speed v measured relative to stationary with respect to Earth, of course, inertial reference frame in figure A. Right, so let's recall Newton's law valid in any initial reference frame. Okay, view this pulse from the different initial reference frame where one that move along with the pulse at the same speed so that pulse appears to be at rest in the frame, which is figure B. Okay, in this reference frame, okay, pulse remain fixed and each element of string move left through pulse shape. Right. Short element of the string of length delta S, okay, forms a proximate arc of a circle of radius R in figure B. Okay. Where in moving reference frame, element of strings move to the left, okay, with speed v. Right. As it travels through arc, model element as particle in circular motion, this element has centripetal downward acceleration equivalent to v squared over r. Okay. And then which is supplied by the T, right, by the T, okay, which is tension within the string. Tx on each side of the element tangent to the arc, right, okay, horizontal component cancel out each other, okay, we only have vertical components, okay, this component towards this add downwards, okay, to 2 times lah. the magnitude of the radial force here, the T here, going to be 2T sin theta. So from here, FR is equivalent to 2T sin theta, more or less to 2T theta, where we consider theta is very small. And the M is equivalent to mu delta S. Okay. Which equivalent to 2 mu r theta. Right. What is a mu? Mu is the mass per unit length of the string. Okay. Mu is the linear mass density, mass per unit length for the string, that particular string. Okay. Elements form part of circle and subtends angle of 2 theta at the center. Why is it? Here. 2 times of theta. Alright. So, delta S itself is equivalent to R times 2 theta. Okay. Element of string model as particle under a net force. We are going to apply Newton's second law to this element in radial direction. Okay, then how is it? F R, because it's moving in circular, kan? And V squared over R, which give us the FR itself is 2T times theta, equivalent to what the M? M is 2 mu R theta V squared over R. Okay, because it's substitution of this. Okay, to this. Right. And not to forget, the V must be squared. Then, cosecant of it, the T is equivalent to mu V squared. If we rearrange this equation, because our interest is to know the speed, the V is equivalent to square root T over mu, where the T is tension within the string here, and mu is linear mass density, where it is equivalent to mass per unit length in SI unit for the string. What is the final unit of this? Still in the unit of it in meter per second, because it's speed, right? Example 16.3. Okay, the speed of a pulse on a cord, a uniform string, has a mass of 0.3 kilogram and a length of 6 meter. The string passes over a pulley and then supports of 2 kilograms, okay, object. Find the speed of the pulse traveling along this string. Okay, so sum of Fy equivalent to T minus M of the block times with the G must equivalent to 0 because it's balanced. From here, okay, T is equivalent to M of the block times with the G. Okay, and we know that V equivalent to square root T over mu, which is our T is equivalent to M of the block times with the G over the mu. M block times G over the mu itself is mass of the string per unit length of it, right? So the V is equivalent to, okay, substitute 2 times 9.8 times 6 over 0.3 kilo, equivalent to 19.8 meter per second. Okay, what if the block was swing back and forth with respect to the vertical like a pendulum? How would that affect the wave speed on the string? Okay, the swinging block is categorized as a particle under a net force, isn't it? The magnitude of one of the force on the block is the tension in the string, which determines the wave speed. As the block swing, okay, the tension change. So the wave speed also going to change. When the block is at the bottom of the swing, the string is vertical and the tension is larger than the weight of the block because the net force must be upward and provide the centripetal acceleration of the block. Therefore, the wave speed must be greater than 9.8 meter per second. When the block is at the highest point at the end of the swing, it's momentarily at rest. So there is no centripetal acceleration and that at that instant. Okay, the block is a particle in equilibrium in radial direction. The tension is balanced by a component of the gravitational force on the block. Therefore, the tension is smaller than the weight and the wave speed is less than 19.8 meter per second that we calculated just now. Okay, example 16.4. Rescuing a hiker. An 80-kilogram hiker is trapped on a mountain ledge. Following a storm, a helicopter rescues the hiker by hovering above him and lowering a cable to him. The mass of the cable is 8 kg and its length is 15 meter. A sling of mass 70 kg is attached to the end of the cable. The hiker attached himself to the sling and then the helicopter then accelerates upward. Terrified by hanging from the cable in mid-air, the hiker tries to signal the pilot by sending transverse pulse up the cable. A pulse takes 0.25 seconds to travel the length of the cable. What is the acceleration of the helicopter? Assume the tension in the cable is uniform. So, what should we do? We should start with this. V equivalent to T over mu. Right? Rearrange. T itself is equivalent to mu V squared. Okay, sum of F is equivalent to MA. And therefore, T minus mg equivalent to MA because it's hanging, right? So this is a person, let's say, the tension is upward, the weight is downward, okay, and the whole system is moving upward. Okay, that is how we have this. Then A is equivalent to T over M minus G, which is equivalent to mu V squared over M, right? Rearrange. Okay, minus G. Okay, which equivalent to mass of the cable V squared over length of the cable times with the M minus G. Okay, this is going to give us, right, M cable over L cable mass delta X over delta T squared minus G. Right then, A itself equivalent to, substitute the value, 8 over 15 times 150 times 15 over 0.25, everything here squared, minus 9.8. Then your final answer of A is equivalent to 3.